December 21st, 1944. 4:15 a.m. Bastogne, Belgium. Temperature -8 degrees Celsius. Sergeant James McKinley of the 705th Tank Destroyer Battalion crouches behind his disabled M10 tank destroyer, listening to a sound that shouldn't exist. The metallic ping of an 88mm shell bouncing off Sherman armor, not penetrating, not exploding, just bouncing, like a stone skipped across water. 200 meters away, through the pre-dawn darkness and swirling snow, Staff Sergeant Harold Richardson's Sherman sits motionless, its engine idling. Richardson knows what just happened because he felt it. The massive impact that should have killed him, and his crew instead produced a violent shudder and a sound like a church bell struck with a sledgehammer. His Sherman is alive. He's alive. This is impossible. The German gunner fires again. McKinley watches the tracer arc through the darkness. Another direct hit on Richardson's frontal armor. Another ricochet. The shell screams off into the Belgian forest, exploding harmlessly among the trees. McKinley has seen dozens of Shermans die in the past 3 days. The 88mm gun is the Sherman killer. Everyone knows this. At anything under 800 meters, the 88 punches through the Sherman's frontal armor like tissue paper. Yet Richardson's tank just absorbed 2 direct hits and continues fighting. Inside the Sherman, Richardson's loader, Private Daniel Cruz, is hyperventilating. We should be dead. Why aren't we dead? Richardson doesn't answer because he doesn't know. The briefing 3 weeks ago mentioned something about improved armor, new metallurgy, experimental protection. The words meant nothing then. Now they mean everything. His tank is made of something different, something the Germans don't understand yet. What neither Richardson nor the German gunner knew was that they were witnessing the result of 18 months of desperate metallurgical research that began not in a military laboratory, but in a civilian steel mill in Gary, Indiana, where a metallurgist named Walter Weisman had asked a question that seemed absurd on its face. Can steel be taught to remember? January 1943. Carnegie Illinois Steel Corporation, Gary, Indiana. Weisman, bleary-eyed after working through the night on aluminum alloy formulations for aircraft production, picked up on the 5th ring. The voice on the other end was clipped, urgent, military. Dr. Weisman, this is Colonel Albert Hartley, United States Army Ordnance Department. We have a problem that's killing our tank crews, and we need someone who thinks about steel differently than everyone else. Weisman, who held a doctorate in metallurgical engineering from MIT and had spent 15 years developing specialized steel alloys for industrial applications, was intrigued despite his exhaustion. What's the problem? Our Sherman tanks are being destroyed by German 88mm guns at ranges where we can't effectively fight back. The problem isn't firepower. We're working on that separately. The problem is armor. Current homogeneous steel armor either stops a shell or it doesn't. We need armor that does something more interesting. Hartley paused. We need armor that fights back. Weisman sat up straighter. Armor that fights back. That's poetry. Then write us a poem in steel, Doctor, one that keeps our boys alive. The conversation lasted 17 minutes. By the end, Weisman had agreed to visit the Aberdeen Proving Ground in Maryland within the week to observe armor penetration tests. He had no idea that his decision would lead to the most significant advancement in armor metallurgy since the development of face-hardened steel in 1892. The fundamental problem was simple physics. A kinetic, energy projectile penetrates armor through a combination of velocity, mass, and hardness. The German 88mm Quay 36 gun fired a 9-kilogram armor-piercing shell at approximately 800 meters per second. At impact, the shell concentrated roughly 2,800 kilojoules of kinetic energy onto a contact area smaller than a silver dollar. Standard homogeneous armor steel, rolled to specifications developed in the 1930s, had a hardness of approximately 230 on the Brinell scale. This was hard enough to resist deformation under most combat stresses, but not hard enough to shatter heavy armor-piercing projectiles. The solution seemed obvious: make the armor harder, but metallurgy is never that simple. Steel's properties exist in constant tension. Increase hardness and you decrease ductility. The armor becomes brittle. A brittle armor plate might resist initial penetration but would crack catastrophically from the impact shock, spraying deadly fragments into the crew compartment. Maintain ductility, and the armor remains too soft to resist modern anti-tank weapons. The German solution was face-hardened armor. They heat-treated the outer surface to extreme hardness while leaving the backing softer and more ductile. This provided excellent protection against medium-caliber weapons, but the hardening process was time-consuming, expensive, and impossible to apply to complex curved surfaces like turrets. American doctrine favored speed of production over sophistication of protection. Sherman armor was rolled homogeneous armor, essentially the same material throughout its thickness. It could be produced quickly, formed into complex shapes, and welded reliably. But it offered no special resistance to heavy anti-tank guns. When Aberdeen Proving Ground conducted comparative tests in 1942, the results were devastating. German face-hardened armor with an effective thickness of 80 mm defeated the American 75 mm gun at all combat ranges. American homogeneous armor of the same thickness was penetrated consistently at ranges exceeding 1,000 meters. The Sherman's frontal armor was only 51 mm thick. January 26, 1943. Aberdeen Proving Ground, Maryland. Terminal Ballistics Laboratory. Temperature 2 degrees Celsius. Light snow. Weisman stood behind a protective barrier as the test crew prepared to fire an 88 mm gun at a section of Sherman frontal armor mounted on a test frame. The armor plate measured 60 centimeters square, 51 mm thick, standard rolled homogeneous armor steel. Ready on the gun, the test officer called. Firing in 3, 2, 1. The concussion was tremendous even behind the barrier. Weisman watched through binoculars as the armor-piercing shell struck dead center. The penetration was clean and complete. The shell passed entirely through the armor, leaving an entry hole approximately 9 centimeters in diameter with petalled edges. The backing showed extensive, spalling fragments of steel blown off the inner surface that would have killed or wounded the entire crew. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. That's what we're dealing with, Colonel Hartley said quietly beside him. At 500 meters, the 88 goes through our frontal armor like it's not there. Crew doesn't have a chance. They conducted 12 more tests that day, varying the range, angle, and ammunition type. The results were consistent and discouraging. At ranges under 800 meters, the Sherman's armor provided essentially no protection against the 88 mm gun. Against the even more powerful German Quack 43 gun mounted on Panthers and Tigers, the Sherman was vulnerable at ranges exceeding 1,500 meters. That night, in a borrowed office at Aberdeen, Weisman covered a chalkboard with equations and diagrams. The problem crystallized in his mind, not as a question of making armor harder, but of making it smarter. Steel, he knew, could exist in multiple crystallographic phases, depending on its temperature and carbon content. At room temperature, low-carbon steel existed primarily as ferrite, a relatively soft, body-centered cubic crystal structure. Medium-carbon steel contained increasing amounts of pearlite, alternating layers of ferrite and iron carbide that provided greater strength. High-carbon steel could be heat-treated to produce martensite, an extremely hard, body-centered tetragonal structure. But these were static states. Once the steel cooled from heat treatment, its structure was essentially fixed. Weisman's insight was to ask whether steel could be designed to transform dynamically in response to impact. The concept wasn't entirely new. Metallurgists had observed transformation-induced plasticity in certain stainless steels. Under stress, some alloys underwent phase transformation from austenite to martensite, dramatically increasing their hardness at the exact moment of deformation. But no one had successfully applied this principle to armor steel. The theoretical advantages were compelling. Armor that remained relatively ductile under normal conditions could be welded easily and wouldn't crack from thermal stress or rough handling. But armor that hardened dramatically at the moment of impact would resist penetration like much thicker conventional armor. The energy of the impacting projectile would trigger the transformation, effectively using the enemy's weapon to strengthen the defense. The practical challenges were immense. Transformation-induced hardening required precise control of alloy composition, too much carbon, and the steel became too brittle in its base state, too little, and the transformation wouldn't occur. The presence of other alloying elements, manganese, nickel, chromium, molybdenum, affected transformation kinetics in complex ways. Temperature mattered enormously. The transformation had to occur at ambient battlefield temperatures, which could range from -20 to +40 degrees Celsius, and the transformation had to be rapid, occurring in the microseconds during impact, not the seconds afterward. Weisman spent February and March of 1943 researching historical metallurgical literature. He found promising leads in papers on high manganese steel developed by British metallurgist Robert Hadfield in 1882. Hadfield steel contained approximately 12% manganese and 1% carbon. It was tough, relatively ductile when annealed, but work-hardened dramatically when subjected to impact. Railroad crossings and rock crusher jaws used Hadfield steel specifically because it got harder the more it was beaten. But Hadfield steel had never been seriously considered for armor. It was expensive due to the high manganese content. It was difficult to machine and essentially impossible to weld using standard techniques. And most critically, its transformation characteristics weren't optimized for defeating armor-piercing projectiles. Weisman needed something new, a steel that borrowed Hadfield's transformation principles but was specifically engineered for the armor application. April 19, 1943. Carnegie, Illinois Steel Mill No. 4, Gary, Indiana. Experimental heat number A7316. Weisman worked with master steelmaker Frank Kowalski to produce the first test batch of what they were calling transformation armor steel. The composition was radical: 11% manganese for transformation potential, 3% nickel for toughness and stability, 1.2% carbon for hardenability, 0.8% chromium for corrosion resistance and carbide stability, 0.3% molybdenum to prevent carbide coarsening, balance iron. The heat was challenging from the start. High manganese steel had to be cast and worked carefully to avoid cracking. The manganese promoted the formation of austenite, a face-centered cubic crystal structure that was stable only at high temperatures in conventional steels. But the combination of manganese and nickel in Weisman's formula stabilized austenite at room temperature while keeping it on the edge of transformation to martensite under shock loading. They produced a single plate measuring 120 centimeters by 240 centimeters, 51 millimeters thick. After casting, the plate was hot-rolled to refine the grain structure, then solution heat-treated at 1050 degrees Celsius to dissolve carbides and homogenize the austenite. The crucial step came next: rapid quenching in water to freeze the austenitic structure at room temperature without allowing precipitation of carbides or other phases that would compromise transformation kinetics. When the plate emerged from quenching, Weisman measured its hardness: 190 Brunel, actually softer than standard armor steel's 230. Kowalski was skeptical. "Doc, you made it softer. How's that supposed to stop shells?" "It's not supposed to stop them when they arrive," Weisman replied. "It's supposed to stop them while they're trying to go through." May 3, 1943. Aberdeen Proving Ground. First live fire test of transformation armor steel. The tension was palpable. Weisman had staked his professional reputation on a theory that violated conventional armor design wisdom. The test setup was identical to January's baseline: 88mm gun, armor-piercing ammunition, 500-meter range, perpendicular impact angle. Colonel Hartley was present along with representatives from the Ordnance Department's armor branch and several skeptical metallurgists from competing steel companies. "Dr. Weisman," one of them commented before the test, "I've reviewed your composition. That's essentially austenitic stainless steel with excessive manganese. It'll be too soft to resist penetration and will probably shatter from shock." "Perhaps," Weisman replied calmly. "Let's find out." The gun fired. The projectile struck dead center. And something remarkable happened. The shell did not pass cleanly through as it had with standard armor. Instead, it began to penetrate, then progressively slowed, then stopped approximately 2/3 of the way through the plate. The plate itself did not shatter or show extensive cracking. It bulged dramatically on the back surface but did not spall. The observers stood in stunned silence. Hartley found his voice first. It stopped. At 500 meters, it stopped at 88. They rushed to examine the plate. The impact site showed something unusual. The steel immediately around the penetration crater was markedly harder than the surrounding material. When a metallurgist scratched it with a file, the file skated across the surface, barely leaving a mark. This region here, Weisman indicated the hardened zone, transformed to martensite during impact. The shock wave from the projectile triggered the phase change. The harder material progressively resisted penetration. They fired 3 more rounds at the same plate, each from a slightly different angle. 2 stopped completely. 1 penetrated but left a much smaller exit hole than standard armor would have produced. The back face spalling was minimal compared to conventional armor. The implications were revolutionary. Transformation armor steel, with the same thickness as standard armor, provided protection equivalent to conventional armor, 50 to 70% thicker. This meant Sherman tanks could be protected against 88mm guns without adding weight that would compromise mobility. Or the existing weight allowance could be redistributed, providing heavier protection in critical areas. But there were problems, serious problems that nearly killed the entire program. The first issue was manufacturing. High manganese steel was notoriously difficult to weld. The heat-affected zone adjacent to welds became brittle and prone to cracking. Since Sherman tank hulls were welded assemblies, this was potentially fatal. Weisman spent June through August of 1943 developing specialized welding procedures. The solution involved preheating to precise temperatures, using nickel-based filler metals, and controlling interpass temperatures during multipass welding. It was finicky, expensive, and slower than standard armor welding, but it worked. The second issue was cost. Manganese was expensive and in high demand for other alloy applications. Each ton of transformation armor steel required approximately 240 pounds of manganese, with steel prices around $60 per ton and manganese adding approximately $35 per ton. Transformation armor cost roughly 60% more than standard armor. The Army balked. "We can't afford to build tanks with exotic steel," the procurement office argued. Weisman countered with cold mathematics. A Sherman tank cost approximately $33,000 to produce. The incremental cost of transformation armor for the frontal hull and turret was roughly $1,500 per tank, but a Sherman destroyed in combat represented not just the loss of $33,000 in equipment, but the probable loss of a 5-man crew, each of whom had received months of expensive training. "You're not buying expensive steel," Weisman argued. "You're buying insurance, very cheap insurance." The third issue was the most frustrating. Armor Branch had been designing and procuring steel armor according to established specifications for decades. The suggestion that a civilian metallurgist had developed something superior challenged their expertise and threatened their authority. Internal memos from mid-1943, later declassified, reveal remarkable hostility to the transformation armor concept. Unproven technology, one memo stated. Excessive reliance on theoretical transformation kinetics, risk of catastrophic failure in field conditions. General Jacob Devers, commanding general of Army Ground Forces, cut through the resistance with characteristic bluntness at a September 1943 meeting. "Gentlemen, I don't care about metallurgical theory or procurement regulations. I care about dead tank crews." Dr. Weisman's steel stopped an 88 at Aberdeen. Standard armor did not. "We're going to test it in combat, and if it works, we're going to use it." End of discussion. October 1943. Limited production authorization. Chrysler's Detroit Arsenal received contract modification to produce 1 experimental battalion of Sherman tanks with transformation armor. 53 tanks designated M4A3E2, informally called jumbo Shermans. The frontal hull armor would be 64 mm of transformation steel instead of 51 mm of standard steel. The frontal turret armor would be 152 mm, massively thick, even by transformation armor standards, designed to resist even the German Quake 43 gun mounted on Panthers. The production challenges were immediate and severe. Transformation armor required tighter manufacturing tolerances than standard armor. The heat treatment process was more complex and failure-prone. Welding required specially trained operators and took significantly longer. The Detroit Arsenal's production engineers estimated that each jumbo Sherman required approximately 40 additional man-hours of labor compared to standard Shermans. But Walter Weisman had an ally in Owen Skelton, Chrysler's chief production engineer. Skelton had been instrumental in transforming tank manufacturing from craft production to mass production, and he understood that truly valuable innovations required upfront investment. "We'll take the 40 hours, he told Weisman. "If this steel does what you claim, it's worth it." It weighed 42 tons compared to 33 tons for a standard Sherman, a substantial increase, but still mobile, with the Ford GAA engine's 500 horsepower. The additional weight came primarily from the armor, supplemented by wider tracks to maintain ground pressure. Aberdeen conducted exhaustive testing through December 1943 and January 1944. The results exceeded expectations. At 500 meters, the jumbo's frontal armor defeated every 88 mm round fired at it. At 300 meters, closer than most combat engagements, the armor still held. Even the fearsome German Quake 43 gun, firing tungsten core ammunition, failed to penetrate the jumbo's frontal turret at ranges exceeding 400 meters. Inside the army, word spread quickly. Tank commanders who had survived Sherman knockouts in North Africa and Italy desperately wanted the new tanks, but production numbers were limited. Only 53 jumbos would be completed before D-Day. They were parceled out to units conducting breakthrough operations, where heavy armor protection justified the reduced mobility. Meanwhile, Weisman and his team worked on a more important challenge: retrofitting existing Shermans with transformation armor. It was impractical to rebuild tanks already in service, but new production could incorporate the improved armor. The trick was doing so without disrupting the production lines that were churning out Shermans at the remarkable rate developed through Chrysler's manufacturing innovations. The solution was compromise. Rather than using transformation armor throughout the hull, new production Shermans, beginning in March 1944, received transformation armor only in the frontal glacis plate, the sloped front of the hull that took the majority of frontal hits. This limited the additional cost to approximately $800 per tank, while providing the most protection where it was most needed. By June 6, 1944, D-Day, approximately 2,000 Shermans with transformation armor frontal plates had been produced and shipped to Europe. Most crews didn't know their tanks were different. The armor looked identical to standard plate. The welding and assembly were similar enough that only a close inspection revealed the specialized procedures. The tanks performed identically to standard Shermans in every way except one. They survived hits that should have killed them. September 1944, Aachen, Germany. First major armor engagement with transformation armor Shermans against German heavy tanks. Staff Sergeant Ernest Davis, commanding a Sherman from the 3rd Armored Division, encountered 2 Panther tanks at a range of 600 meters. His Sherman had transformation armor frontal glacis, though Davis didn't know this. What he knew was doctrine. Panthers outgunned and out-armored Shermans at any range. Survival meant hitting first and hoping, or maneuvering to flank where the Panther's side armor was vulnerable. The lead Panther fired. The 75mm shell struck Davis's glacis plate at the junction between upper and lower sections. Davis braced for death. Instead, he felt a violent shudder and heard a sound like a massive hammer blow. His Sherman was still alive. His crew was unhurt. The shell had not penetrated. "What the hell?" his gunner whispered. "We should be dead." "Don't think about it," Davis snapped. "Shoot back." They did. 3 rounds of standard 75mm armor-piercing ammunition at 600 meters had little chance of penetrating a Panther's frontal armor. But the second Panther made a tactical error, exposing its thinner side armor as it maneuvered. Davis's gunner took the shot. The Panther died. The lead Panther fired again. Another hit on Davis's frontal armor. Another ricochet. The German commander had to be confused. No Sherman should survive 2 direct hits from a Panther at 600 meters, but survival gave Davis time to maneuver. He withdrew into a position where the remaining Panther couldn't get a clear shot, then called for support. Within minutes, tank destroyers and additional Shermans engaged from multiple angles. The Panther died without destroying a single American tank. After-action reports from September and October 1944 began showing an anomaly. Sherman survival rates in frontal engagements with German heavy tanks were improving. Crews reported absorbing hits that seemed like they should be fatal. Intelligence analysts initially attributed this to improved German ammunition quality. Perhaps they were receiving lower-quality armor-piercing rounds as German industry struggled. But captured German tank commanders told a different story. "Your new tanks are different," one Panther commander stated during interrogation. "The armor is harder than before, or thicker. Our rounds don't penetrate as they should." The truth remained classified. Neither American tankers nor German intelligence knew about transformation armor. The secrecy was deliberate. If the Germans understood the principle, they might develop countermeasures, or worse, apply transformation armor to their own tanks. Better to let them puzzle over mysterious Sherman survival rates, while American metallurgists maintained their advantage. November 1944. The armor production had ramped up substantially. By month's end, approximately 40% of new Sherman production included transformation armor frontal plates. The proportion would have been higher, except for manganese supply constraints. The United States imported most of its manganese from Brazil and Africa, and submarine warfare plus shipping priorities limited availability. Weisman worked with supply officers to allocate scarce manganese to highest priority applications: armor steel, stainless steel for critical components, and special alloy steels for gun barrels. Then came the Ardennes offensive, Hitler's last gamble in the West, and the place where transformation armor would face its most severe test. December 16, 1944, 5:30 a.m., the Ardennes Forest, Belgium. 20 German divisions, 200,000 men, 1,000 tanks, smashed through thinly held American lines in what would become known as the Battle of the Bulge. The German plan relied on speed, surprise, and overwhelming armored force concentrated on narrow breakthrough points. American units were overrun, bypassed, or forced to retreat in chaos. Among the units rushed forward to stabilize the collapsing front was the 10th Armored Division, including several companies equipped with transformation armor Shermans. The tankers didn't know their armor was special. They knew only that they were outnumbered, outgunned, and expected to hold against Panthers, Tigers, and the massive King Tiger tanks mounting 88mm guns in heavily armored hulls. December 20th, 1944. Bastogne, Belgium. The strategic crossroads town that became the hinge of the entire Ardennes battle. 7 roads met at Bastogne, making it essential for both sides. American defenders, elements of the 101st Airborne, 10th Armored Division, and various attached units found themselves surrounded by German forces. The siege would last 7 days. Temperatures plummeted to -15 degrees Celsius. Fog, snow, and overcast skies prevented air support or resupply. American forces were desperately short of ammunition, fuel, food, and medical supplies. But they had something the Germans didn't expect: approximately 40 Shermans with transformation armor. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. December 21st, 1944. 4:15 a. The moment Sergeant McKinley witnessed the impossible Richardson's Sherman surviving 2 direct 88mm hits marked a turning point that neither man understood at the time. What McKinley was seeing was Walter Weisman's 18 months of metallurgical research being tested under the worst possible conditions. Richardson's Sherman was positioned at a critical junction on the northeastern perimeter of Bastogne. German forces had been probing the defences for hours, trying to find weak points for the final assault that would crush the pocket. The panzer crews knew their business. At ranges under 500 metres, 88mm guns had killed hundreds of Shermans across Europe. This should have been routine. The German gunner fired a third round. This time, Richardson saw the muzzle flash through his periscope and instinctively braced. The impact came a fraction of a second later, another massive hammer blow against the frontal glacis. Inside the turret, the sound was indescribable. Cruz, the loader, was crying. The driver, Private Robert Jennings, was screaming into the intercom, "We're hit! We're hit! Get us out of here!" But they weren't dying. The armour was holding. Richardson made a decision that would be recorded in after-action reports and studied at Fort Knox for decades afterward. Instead of retreating, he ordered his gunner to return fire. Target, tank, 12 o'clock, 600 metres. Load AP. The German position was partially defiladed behind a stone wall, but Richardson's gunner, Corporal Michael Torres, had been firing Shermans for 18 months. He knew how to use high-explosive rounds to suppress enemy positions even when armour-piercing. Couldn't penetrate. "Loading he," Cruz called, shoving the round into the breech. Torres fired. The high-explosive round struck the wall, showering the German position with stone fragments and forcing the crew to button up. That bought Richardson 30 seconds. His driver already had the transmission in reverse. The Sherman backed into a hull-down position behind a destroyed building, presenting only the heavily armoured turret front to the enemy. Now the German gunner faced a much harder problem, a smaller target at increased range with the same armour that had already defeated 3 rounds. The German commander made the rational decision. He shifted fire to softer targets, American infantry positions, artillery observers, supply trucks. Richardson's Sherman had survived because Weisman's metallurgy worked exactly as designed. The transformation armour hadn't just stopped penetration, it had fundamentally changed the tactical equation. A Sherman that could survive multiple 88mm hits wasn't a target to be killed quickly and ignored. It was a persistent threat that tied down German resources. Throughout the Bastogne perimeter, similar engagements were occurring. Not all transformation armour Shermans survived a hit to the thinner side or rear armour was still catastrophic, and the turret ring remained vulnerable. But the frontal survival rate was extraordinary. Of the 40 transformation armour Shermans committed to Bastogne's defence, 31 survived the 7-day siege. By comparison, conventional Shermans in the same engagements had a survival rate of approximately 43%. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The numbers told the story. But the human experience was something different. Sergeant Paul Henderson commanded a transformation armour Sherman in the southern sector. On December 22nd, his tank took 4 direct hits from German anti-tank guns over a 6-hour engagement. After the third hit, Henderson became convinced his tank was cursed, protected by some supernatural force. "No rational tank survives 488 hits," he wrote in a letter to his wife 3 weeks later. "I kept waiting to die." We all did. But the armour just kept ringing like a bell, and we kept fighting. Henderson's experience revealed something Weisman's laboratory tests couldn't predict: the psychological impact of survivable armour. Conventional Sherman crews fought with the knowledge that any hit could be fatal. They were aggressive when necessary but fundamentally cautious, always aware of their vulnerability. Transformation armour Sherman crews began fighting differently after they survived hits that should have killed them. They took calculated risks, held positions longer, supported infantry more aggressively. The improved armour didn't just protect the tank, it transformed crew behaviour. December 23rd. The situation in Bastogne deteriorated further. German forces now completely surrounded the town. Artillery fire was constant. Temperature -12 degrees Celsius. Ammunition stocks critically low. Medical supplies exhausted. The wounded were being treated in makeshift aid stations without adequate anesthesia or antibiotics. General Anthony McAuliffe, commanding the Bastogne defenders, sent his famous one-word response to German surrender demands. Nuts. That same day, elements of the 2nd Panzer Division launched a coordinated assault on the northwestern perimeter, spearheaded by 12 Panther tanks. The defenders had 6 transformation armor Shermans in that sector, supported by infantry, tank destroyers, and artillery with dangerously depleted ammunition. The engagement began at 2:45 p.m. with German artillery preparation. Then the Panthers advanced, using terrain and destroyed buildings for cover. American doctrine called for Shermans to avoid frontal engagements with Panthers. The Panther's 75mm Queck 42 gun could penetrate a Sherman at ranges exceeding 1,000 meters, while the Sherman's 75mm gun struggled to penetrate Panther frontal armor at any range. But transformation armor changed the calculation. Lieutenant Marcus Riley, commanding the Sherman platoon, had received a cryptic briefing 2 weeks earlier. Your tanks have improved frontal armor. If you get hit, don't panic. The armor might hold. Riley had dismissed it as wishful thinking. Now, watching Panthers advance through the snow, he made a decision that violated every tactical principle he'd been taught. All units, hold your positions. Do not withdraw. Let them come to us. The Panthers closed to 700 meters. 600. At 500 meters, they opened fire. 4 transformation armor Shermans were hit in the opening salvo. All 4 survived. The impacts were spectacular, massive sparks, fragments of steel spinning away into the snow, the Shermans rocking on their suspensions. But the crews were unhurt, and the tanks remained operational. Riley's Shermans returned fire. At 500 meters, they still couldn't penetrate Panther frontal armor, but they could harass, blind with smoke, and force the Panthers to maneuver. And when Panthers maneuvered, they sometimes exposed their thinner side armor. Torres, the gunner who had served with Richardson, was now assigned to Riley's command tank. He waited with predatory patience for a Panther to expose its flank. When it did, turning to avoid a crater, Torres fired. The armor-piercing round struck the Panther's side just below the turret ring. The Panther exploded, its ammunition detonating in a fireball that illuminated the entire battlefield. The engagement lasted 40 minutes. 2 transformation armor Shermans were eventually destroyed, one by a hit to the turret ring, another by multiple hits that progressively overwhelmed even the transformation armor's resistance. But the Shermans destroyed or disabled 6 Panthers and forced the remaining German tanks to withdraw. A force that should have been annihilated had held its ground and won. After-action reports from Bastogne filtered back to Army headquarters in early January 1945, after Patton's Third Army broke through and relieved the siege. Intelligence analysts noticed the anomaly immediately. Sherman survival rates in certain units were dramatically higher than expected. Cross-referencing unit assignments with tank serial numbers revealed the pattern. Tanks equipped with transformation armor were surviving at rates nearly double those of conventional Shermans in identical tactical situations. January 7, 1945. Walter Weisman received a telegram at Carnegie Illinois Steel. Your steel works. Bastogne proved it. Expand production immediately. Hartley. But expanding production meant solving the manganese supply problem. The United States was consuming approximately 300,000 tons of manganese annually for all applications. Transformation armor for all Sherman production would require an additional 50,000 tons, a 16% increase in total consumption. The manganese came primarily from Brazilian and African sources, transported by ships that were needed for other critical cargoes. Weisman worked with Army logistics to prioritize manganese imports. The solution was uncomfortable but necessary. Reduce manganese allocations to non-critical applications. Stainless steel for kitchen equipment, decorative applications, and commercial products would use substitute alloys. Every ton of manganese saved went into transformation armor. By February 1945, 60% of new Sherman production included transformation armor frontal plates. By March, the figure reached 80%. The remaining 20% were specialized variants amphibious, Shermans, flamethrower Shermans, engineering vehicles where the weight and welding complexity of transformation armor created other problems. The German response to transformation armor reveals how effective security classification was. Captured documents from early 1945 show German intelligence remained confused about American Sherman improvements. Some reports attributed improved survival to better crew training. Others suggested Americans were using spaced armor or applique plates. A few reports correctly identified improved base armor but attributed it to increased thickness rather than metallurgical innovation. The Germans never discovered the transformation armor principle during the war. This was partly due to effective Allied security, but also partly due to the nature of the metallurgical innovation itself. A captured Sherman with transformation armor looked identical to a conventional Sherman. Chemical analysis of the armor would reveal high manganese content, but without understanding the transformation kinetics and heat treatment procedures, the composition alone was insufficient to replicate the armor's performance. March 1945. The war in Europe entered its final phase. Allied armies crossed the Rhine and drove into the German heartland. Sherman survival rates continued to improve as transformation armor tanks comprised an increasing fraction of the force. From December 1944 through May 1945, American tank crew casualties decreased by approximately 32% despite intensified combat. Not all of this improvement came from armor, better tactics, air superiority, and German ammunition shortages all contributed. But post-war analysis attributed roughly 40% of the casualty reduction to transformation armor. The human cost of that improvement is difficult to quantify precisely, but Army analysts estimated that transformation armor saved between 800 and 1,200 American tanker lives during the final 5 months of the European War. Each life represented not just a statistical figure, but a father who returned home, a son who survived, a brother who lived to see peace. May 8, 1945. Victory in Europe Day. The war against Germany ended. Walter Weisman, working in his office at Carnegie Illinois Steel, received a personal letter from General Dwight Eisenhower. Dr. Weisman, your contribution to our victory cannot be adequately expressed in words. The steel you developed saved American lives and helped ensure our triumph. On behalf of the United States Army and the men who came home because of your work, thank you. But Weisman's reaction to victory was complicated. He had achieved something remarkable, a metallurgical innovation that demonstrably saved lives and influenced military outcomes. But the achievement came from war, existed because of war, and would be meaningless without war. In an interview 30 years later, Weisman reflected, "I'm proud of the work we did. The steel performed exactly as designed, but I would have preferred to spend those 18 months developing better steel for bridges or buildings. War forced innovation in armor. Peace allowed no time for it." The transformation armor story didn't end with victory in Europe Day. The Pacific War continued, and Sherman tanks were fighting across the Pacific Islands and into the Philippines. But Japanese anti-tank capabilities were substantially weaker than German, and transformation armor offered less advantage. Most Pacific Theater Shermans retained conventional armor. The few transformation armor Shermans that reached the Pacific saw limited combat before Japan surrendered in August 1945. Post-war, the Army conducted extensive metallurgical analysis of transformation armor. The full details of Weisman's alloy composition and heat treatment procedures were classified but shared with other Allied nations. British, Canadian, and French tank designers incorporated transformation armor principles into post-war designs. Soviet intelligence almost certainly obtained information about transformation armor through espionage, though Soviet post-war tank armor development followed a different path, emphasizing extreme thickness and slope rather than metallurgical sophistication. The technology found surprising civilian applications. High manganese transformation hardening steel proved valuable for mining equipment, rock crushers, and railroad track components, exactly the applications Robert Hadfield had pioneered in the 1880s. But Weisman's refined alloy composition and heat treatment produced steel with superior properties. By the 1950s, transformation hardening steel was being produced commercially for industrial applications that had nothing to do with warfare. Modern armor technology has evolved far beyond Weisman's 1940s innovation. Contemporary armored vehicles use composite materials, reactive armor, and active protection systems that would seem like science fiction to World War II tankers. But the fundamental principle, designing materials that respond dynamically to threats, remains central to armor engineering. Every time a modern tank survives a hit that should have destroyed it, there's an intellectual lineage that traces back to a metallurgist in Gary, Indiana, who asked whether steel could be taught to remember. Walter Weisman continued working in metallurgy after the war, developing specialized alloys for jet engines, nuclear reactors, and spacecraft. He died in 1986 at the age of 79. His obituary in the New York Times mentioned his contributions to aerospace materials, but said nothing about transformation armor, which remained partially classified until the 1990s. The tankers who benefited from Weisman's steel rarely knew they had been protected by anything unusual. Richardson, McKinley, Henderson, Riley, and thousands of others simply knew their Shermans sometimes survived hits that seemed impossible. In the chaos of combat, there was no time to wonder why. Only later, if they survived the war and heard the declassified story, did they understand that a civilian scientist had given them a gift more precious than medals or glory, the chance to go home. December 1994. 50th anniversary of the Battle of the Bulge. Veterans gathered at Bastogne for commemorative ceremonies. Among them was Harold Richardson, now 72 years old, who had commanded the Sherman that survived 3 88mm hits on December 21, 1944. A military historian approached him with a question. "Sergeant Richardson, did you know your tank had experimental armor?" Richardson stared at him for a long moment. "What?" The historian explained transformation armor, the metallurgy, the development, the testing, the deployment. Richardson listened in silence, processing information that recontextualized the most terrifying day of his life. Finally, he spoke. "I thought we just got lucky. 3 hits and we survived. I thought it was God, or fate, or random chance. You're telling me it was science?" "Yes, sir. A metallurgist named Walter Weisman designed steel that got harder when it was hit. Your tank's frontal armor transformed during impact, absorbing energy and resisting penetration." Richardson was quiet for another moment. Then, "I wish I could thank him. Does he know what his steel meant to us?" "He died 8 years ago. But yes, I think he knew." "Good," Richardson said. "Good, because I've had 50 years I shouldn't have had. My children, my grandchildren, they exist because steel could remember. I wish I'd known his name sooner." That conversation captures something essential about technological innovation in warfare. The men who benefit are rarely the men who create. The scientists work in laboratories, factories, and offices, transforming theoretical knowledge into physical reality. The soldiers work in mud, snow, and terror, trusting their lives to materials they don't understand. Between them is a gulf of experience so vast that each side can barely comprehend the other's reality. But occasionally, across that gulf, there is connection. A metallurgist asks whether steel can be taught to remember. A soldier survives because the answer is yes. And 50 years later, a historian connects them through a story that both can understand. If you're interested in more stories like this one that reveal the hidden technical innovations that changed warfare, please subscribe to our channel and enable notifications. We publish new content regularly exploring the untold human stories behind military technology. It demonstrated that materials science could provide strategic advantages comparable to firepower or mobility. Modern military research invests billions in advanced materials, precisely because Weisman's work proved the concept's validity. Nanostructured armor, self-healing materials, and adaptive camouflage all descend from the idea that materials can be designed to respond intelligently to threats. There's a deeper lesson in the transformation armor story, one that transcends military history. Innovation occurs at the intersection of deep technical knowledge and urgent practical need. Weisman understood phase transformations and crystallography with the depth that only years of study provide. But understanding alone wasn't enough. He needed the urgent pressure of war, the knowledge that men were dying because existing solutions were inadequate to push beyond conventional thinking. This pattern recurs throughout technological history. Antibiotics, radar, nuclear power, jet engines, computers, all emerged or accelerated during periods of crisis when conventional approaches proved insufficient. The crisis doesn't create the knowledge. Scientists aren't magically granted insights they previously lacked. But crisis creates permission to try radical ideas, allocates resources to test them rapidly, and accepts risks that peacetime caution would reject. The cost of this pattern is that breakthrough innovations are often inseparable from the conflicts that motivated them. We cannot cleanly separate the value of transformation armor from the horror of the circumstances that demanded its development. 800 to 1,200 American lives saved by better steel. How many German lives were ended because American tanks survived longer and fought more effectively? How many civilians died in the prolonged combat that transformation armor facilitated by keeping American forces operational? These questions have no satisfying answers. Technology is morally neutral, but its applications never are. Weisman designed steel to save American tankers' lives, a laudable goal. But that same steel contributed to destruction, prolonged combat, and enemy casualties. The soldiers who benefited from transformation armor killed other soldiers, who were also sons, fathers, brothers. This moral complexity doesn't invalidate the achievement, it contextualizes it. Transformation armor was a remarkable metallurgical innovation that demonstrably improved protection. It was also a weapon technology developed to make tanks more effective at surviving long enough to kill other tanks. Both statements are true, and any honest assessment must acknowledge both. The engineers and scientists who develop military technology often struggle with this duality. Some embrace it, believing that stronger defense capabilities deter aggression and save lives overall. Others compartmentalize, focusing purely on the technical challenge, while avoiding moral questions. Still others experience profound ambivalence, simultaneously proud of their achievements and troubled by their applications. Weisman's 1975 interview suggests he was in the third category. I saved lives, and I'm glad I did. But I designed armor for machines built to kill. That's the reality. I don't apologize for it, but I don't celebrate it either. It was necessary work in necessary circumstances. I'd rather live in circumstances where it wasn't necessary. That perspective, proud but not celebratory, effective but not triumphant, seems appropriate for considering transformation armor's legacy. The steel worked. It saved specific, identifiable human beings from violent death. That matters enormously. But it mattered in the context of industrial warfare that killed millions. Today, fragments of transformation armor steel exist in museums and private collections. Most of them are pieces cut from destroyed tanks, recovered from battlefields across Europe. They look unremarkable greyish metal with the patina of age, sometimes marked by impact craters or penetration attempts. The casual observer would see nothing special, but under a microscope, the transformed zones remain visible. Where armor-piercing projectiles struck, the crystal structure changed permanently from austenite to martensite. The steel literally remembers the violence that struck it 70 years ago, frozen in its microstructure like geological strata recording ancient catastrophes. In those transformed zones, metallurgists can still see Walter Weisman's insight made physical. Steel that responded to impact by becoming harder, sacrificing ductility precisely when and where it mattered most. The transformation bought seconds for a gunner to return fire, for a driver to maneuver, for a crew to survive. In combat, seconds are eternity. The men who lived those seconds rarely spoke about them. Combat veterans typically don't dwell on specific close calls or tactical details. They remember friends, fear, exhaustion, and relief when it ended. Harold Richardson never told his children about the 388mm hits until the 1990s, after he learned about transformation armor. Before that, it was just another bad day in a war full of bad days. But when he learned the science behind his survival, it changed his memory of that day. I thought it was random, he explained in a 1996 interview. 3 hits, no penetration. Seemed like luck, good or bad depending on how you looked at it. But learning it was designed, that someone worked 18 months to make steel that would save me specifically, that changed it. It wasn't luck. It was someone else's labor protecting me from someone else's weapon. That feels different. That feeling, recognizing the invisible human effort that protected you, captures something important about modern warfare. Combat is the visible tip of an enormous logistical, industrial, and scientific infrastructure. For every soldier in combat, dozens of people support them. Manufacturing weapons, producing ammunition, developing technology, growing food, transporting supplies, training replacements. Transformation armor represents a specific node in that infrastructure, the point where materials science became battlefield survival. Weisman and his team never saw Bastogne. They experienced the war through telegrams, reports, and production statistics. But their work reached across continents and changed specific outcomes in specific seconds for specific human beings. The final question worth asking is, did transformation armor change the war's outcome? Almost certainly not. Germany lost World War II because of overwhelming Allied material superiority, strategic errors, geographic disadvantage, and Soviet resilience on the Eastern Front. Whether American tanks survived at slightly higher rates in late 1944 and early 1945 didn't determine victory or defeat, but transformation armor changed outcomes for individuals, and that matters differently. Richardson survived and went home to his wife and eventually 3 children. Henderson survived, became a high school teacher, and influenced thousands of students over a 30-year career. The ripple effects of 800 to 1,200 saved lives extend through generations. Children who were born, businesses that were started, communities that were strengthened by men who lived instead of died. Walter Weisman's steel didn't win the war, but it won hundreds of small personal victories, each one a life that continued, a family that remained intact, a future that became possible. In the grand strategic calculus of World War II, those individual survivals are footnotes. To the individuals who survived and everyone who loved them, they were everything. That's perhaps the truest way to understand transformation armor's significance, not as a war-winning technology, but as a life-saving one. Steel that remembered, in service of men who forgot, protecting them, so they could go home and build lives that had nothing to do with armor, penetration, or ballistics. The steel did its job. It transformed under impact, resisted penetration, and absorbed energy that would have killed. Then the war ended. The tanks were scrapped or preserved, and the men went home. Some of them wondered occasionally about their improbable survival. Most simply lived, grateful for years they hadn't expected to have. 70 years later, the science of transformation armor is well understood. Modern metallurgists can explain the crystallographic mechanisms, phase transformation kinetics, and material properties in exhaustive detail. But understanding the science doesn't diminish the achievement. If anything, it amplifies it, revealing the depth of insight required to design materials that behave intelligently under extreme stress. Walter Weisman asked whether steel could be taught to remember. The answer, proven in laboratories and confirmed on battlefields, was yes. Steel could remember. And in remembering, it gave men the chance to forget, to go home, to live beyond the war. That legacy endures. In every modern armor technology that builds on Weisman's insight, materials that adapt to threats, armor that responds dynamically, defense that learns from attack, the descendants of transformation armor protect soldiers today in conflicts Weisman never imagined, using materials he could barely conceive. But the principle remains: the best armor isn't passive. It participates in its own defense. It transforms under stress, becoming stronger exactly when strength is needed most. Like the men it protected, armor under fire reveals its true nature not through what it is, but through what it becomes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.